Good afternoon, everybody. We are very lucky today to have Professor Alex Halliday from Oxford University to give us a talk on the origin of the Earth-like planets. Professor Alex Halliday spent 12 years as a professor at the University of Michigan and then 6 years at the ETH in Zurich as the head of the Earth Science Department. And now, from year 2004, he took up the chair of the geochemistry at Oxford, and now he's the head of the division of maths, physics, and life science. He is a world leader in utilizing isotope methods to study the Earth and the planetary processes, and has published over 300 peer-reviewed articles, including 40 in Science and Nature, the two top journals in natural sciences. With his success in technological innovation, Professor Halliday uses mass spectrometry to elucidate the origin and the early development of the solar system and the recent Earth processes such as continental erosion and climate. In addition, he is also engaged in studies of the mechanism of volcanic eruptions, the formation of minerals, and the hydrocarbon deposits, and the development of civilization. Professor Halliday has been president of the American Geochemical Society and the European Association of Geochemistry. He has experience with a range of top science boards and advisory panels, currently including those of the Natural Environmental Research Council, the Natural History Museum London, the Max Planck Institute for Chemistry in Mainz, Germany, and the American Geophysical Union. Professor Halliday's scientific accomplishments have been recognized with awards from several scientific societies. He was elected as a Fellow of the Royal Society in year 2000. Alex, thank you very much for your
Thank you very much indeed. Can you all hear me okay? So thanks for a very nice introduction. That was a glowing introduction. I wanted to talk to you today about some of the research I've been doing for the last 15, 20 years. I started life as a geologist, and I always wanted to be a geologist since I was a teenager. And I was brought up by my aunt, and she did not know what to do with me. So she used to take me out on mine dumps looking for minerals, and she thought I'd be interested in minerals. So that's how I ended up becoming a geologist. But I've always been fascinated by astronomy and planets. And 20 years ago, we started moving into a new area of mass spectrometry, and I acquired the first mass spectrometer of its kind in the world. And I realized it would allow us to do things other than just dating rocks in the way that we had been doing up until then. It would allow us to actually open up the whole periodic table for study and explore some isotopic systems that would allow us to actually look at the origin of the solar system and the timescales for the formation of planets. So today what I'm going to do is talk mainly about the solar system and how it forms. I'm going to try not to be too technical. If any of you want to interrupt and ask a question, that's fine. If I'm going too fast for some of you. But I'll try and keep it fairly light. I won't show very much, won't show any equations, and I probably won't show very much data, just a little bit of data, just because data still excites me, and I'm sure it excites you as well. So this introductory slide is just a beautiful slide of an eclipse of the sun, and it basically reminds us that we're part of a solar system, and that these objects, the Earth and the Moon, are very intimately connected. And a large part of what I've been doing is to basically try and understand how the Earth and Moon are connected and how they relate to the birth of the Sun. And that's what I want to talk to you about today. This is my research team at Oxford. We're still growing and shrinking because people keep getting jobs. But it's a sizable team working on a variety of elements. And this shows you the various elements that we're mainly focusing on at the moment at Oxford University. And at ETH we had a different set of elements, and prior to that we worked on different elements in Michigan. We've just moved into a new Earth Sciences building at Oxford. So I know Don Malthus has actually been there and seen this. This does not look. This is not an architectural error. Okay, this is meant to look like geological strata. So it's a bit different from most Oxford buildings that are built rather classical style. And this is the lab wing here, which includes the biggest suite of isotope geochemistry labs of their kind in the world, a big suite of clean rooms. And then we have an office block over here, and we have places for lectures underneath here. So if you're coming through Oxford, please come by and take a look. I want to talk about, most of everything I'm going to talk about today involves a subject called, a technique called multiple collector ICP-MS, which is MCICP-MS for short. And as I said, we acquired the first instrument in the early 90s in Michigan, and this shows you the growth in the number of talks that followed that first instrument. And the whole subject has expanded dramatically. We stopped counting after 2004. And now many laboratories around the world have got this kind of instrument. There's several hundred instruments worldwide. I noticed you've got one here in Hong Kong University. They're incredibly versatile. And the reason why they're so successful is that if you look back at a university like Oxford some 15, 20 years ago, then the elements shown in red here would have been the kinds of elements that you would have been working on in isotope geochemistry, trying to explore the natural isotopic variations in the Earth. And the reason was primarily because they were the ones you could really measure relatively easily with the techniques around. Today, it's quite different, and the variety of isotope geochemistry laboratories around the world are tackling different elements. But you can actually pretty much explore the whole periodic table to very, very high precision. We can measure high precision isotopic variations in small natural samples, small amounts that we find in natural samples. We can measure high precision isotopic variations in things with very high first ionization potential, like tungsten, for example, which I really want to work on, which couldn't be analyzed before. And this has allowed us to explore everything pretty much in the periodic table, even in a few nanograms of material. So the laboratory we've built in Oxford basically has an old machine here. It's a very large machine built by Keith Irons, which is 20 years old, which we're changing, and we're putting a new plasma source on it to make it into a large geometry multiple collector ICP-MS. And then we've got 4 multiple collector ICP-MSs, that's 2 new ones and 2 old ones. With the taking delivery of another multiple collector ICP-MS, we'll have 6 multiple collector ICP-MSs in Oxford. Then we've got 3 single collector instruments as well for doing elemental analysis, and then a variety of other kinds of instruments for building the research. We're supported by a whole variety of funding councils. This is the SDFC, European Research Council, Natural Environment Research Council. We've received a lot of money from Petrobras. Oxford itself has put money in, and I should have put the Royal Society in here, they can contribute as well. So let's put the talk in its context and first start talking about solar systems and how they form. This is our solar system. This is the inner solar system. So you can see here the terrestrial planets, which start off with Mercury, then Venus, then Earth, then Mars going out. These are all small objects. They're very high density. They're rocky. They're mainly made of silicate and iron. Then outside that, you can see that you've got the asteroid belt, and then outside that, you've got the big gaseous and icy planets, Jupiter and Saturn, and then beyond there, you've got Neptune and Uranus that are basically more like icy objects. And Pluto's kind of weird, maybe it's classified, but it's really part of the cometary objects that you see. Now, that solar system basically, as you know, forms from something like a disk. It was first proposed a couple of hundred years ago by Count and Laplace and two different sets of papers, but actually the solar system formed from an evolving, rotating disk of gas and dust, and that's the natural result of a collapsing cloud that actually formed the sun. As the angular momentum basically gets transferred into the disk around the star as the cloud collapses. We can see these disks forming around other stars today. So this is the Orion Nebula in the constellation Orion, which is probably the brightest, one of the most easy and best known constellations in the sky. And you can see here two objects, M42 and M43. And if you zoom in on those, these are actually visible to the naked eye. As you zoom in, you find these are very, very bright areas of gas and dust that are being illuminated by stars that are forming. So I'm going to zoom in closer and closer into this region here. The screen tilts around, I'm afraid, point of view as you move in. And as we move into this region here, you can see there's four very bright stars there. If you close in on those a little bit closer, here they are, you can see that the gas and dust around there has got some other objects in it as well. And in particular, it's got these small things that don't quite look like stars, but they look like sort of gaseous, sort of dusty sort of objects. If you move in even closer, you can see that they start to look like this. And then as you get in closer still, you can see they're actually like this. They're actually sort of disc-shaped. And these are brand new stars. They're less than 1 million years old. And they're just forming. And they're still opaque because there's all that dust still wrapped around them in a sort of quasi-disk type object. Here's a couple more that actually show some of the luminosity from the star itself. This is a nice edge-on view of a star with the opaque, dusty disk around it. And this is how we think our solar system started, as planets that grew from these dusty disks. And we've got a variety of observational evidence for how long these disks last. We think they last less than 10 million years, with an average half the mass is probably gone in about a couple of million years, so they gradually accrete onto the star, and they leave behind planets that are accreting at the same time. So this is an artist's impression of what a disk looks like. It's pretty much the same as people have always thought a disk looks like, except for one thing, and that's these bipolar outflows, which are very, very energetic jets of material that extend over parsecs, which people have got a variety of theories for what those are about. But these are very, very dynamic systems. So sort of the disk is actually being accreted onto the star. Sometimes it's injecting large amounts of material in the process. And there's a variety of exciting physics going on here in terms of radiation and fields being developed, which will eventually affect the way the planets and the dust actually end up forming. And we've actually observed some of this stuff ourselves in the laboratory by looking at meteorites that represent part of that dusty disk from 4.5 billion years ago in the case of our own solar system. So when you hold your camera open on a nice starlit night and leave it open for a while, the shutter open for a while, you can see as the Earth rotates, you get these little star trails left as the Earth is rotating. And then across the field of view, you suddenly get a very bright illuminated object. That's a shooting star. And it's actually made up of some kind of a meteorite that's actually going to land on Earth, hopefully. It doesn't completely burn up. There's about 50 million kilograms of this stuff landing on the Earth every year. You don't notice it on a day-to-day basis. Most of it's coming down as very, very fine dust, and it's being destroyed or it's being left on the surface of the ocean, just as very, very fine dust. And it's only occasionally you get something quite nasty that wipes out dinosaurs. So the most common kind